So let's actually talk about GANs because we kind of cover it a bit. So for the GANs, as we saw for AAE, the task or the job is what is fake, and what is real, and how can I find it? How can I tell what is the real data, what is fake data? So that's what. So the GAN has like two components. One of them is generator, which will try to create a new sample based on so based on some knowledge which it will learn from the learning process, from the training process of the model. The other one is a discriminator, which will try to predict which sample is real or not real, which is fake or real. So and then you're saying that these the GANs, just using these two components and playing with some adversarial technique, it will learn the probability distribution of your training data, and uh, then by kind of imposing some restriction in the discriminator part, you should be able to kind of recreate some image which is sounds like real data as well. So here, if you maybe maybe 5 GANs got super famous because the generator part was able to generate a sample which was super close to the real data, because here the idea is the generator part, just by given, let's say, random noise, that random noise can be your prior as well. So here you can define your prior, something similar to VAE and AE that we define, and based on that you're creating an image, or because here is like an MNIST image, or it can be any sample data, which will be like a fake image for us. And then you have a sample from your data as well, and the only job that this discriminator has is to be able to tell the difference. Say, okay, that's a real one and that's a generated one. So here, so the modeling part, the generator part, are supposed to learn the data. And then what will happen and then you can say the discriminator part is okay. It is a judge here. The judge, we should say what is real, what is fake, and if something is not from your training distribution, or if the fake one is not similar to your training data, the discriminator should be able to catch it and say, oh, you're not from the data, and then be able to say that, okay, maybe you're outlier for us because you're looking for outlier. And based on this simple technique, we should be able to find an anomaly detection as well. So I'm gonna just say it again as well. Usually for GANs, they're mainly looking for a good generator to be able to make kinda like a real data, which is super similar to the actual training data. And then the discriminator is there to be able to tell the difference and enforce the generator to get better and better and better. Because as far as the discriminator can tell the difference, the generator will have a huge loss, and then it has to change its parameter to be able to make a better and better and better sample data. So here we're just, instead of just talking about generator for anomaly detection, we want to talk about actually the discriminator, which for us here will be like a supervised model. Given a sample, it has a binary prediction, 0 or 1. In the previous session, I said I'm gonna make a new make like a stepping stone for this lecture. And back then I said, if I have a training set, which like here, which will be basically all real, for that session it was all pure credit card data, and I said, if I manually create a bunch of generated data just by shuffling all these columns, from that moment, if I have only this discriminator part to be able to tell the difference, so that I was able to kind of get good number just by having a discriminator part of the GANs, and me as a human by some algorithm which was shuffling to coming up with some fake data. Here, this difference is the generator and the discriminator are more, I would say, a more sophisticated version of the thing that you have done. So it means instead of doing shuffling, the generator will try to make a new sample, and if the discriminator can't tell the difference, the generator has to come up with a better way of making a fake image or fake sample. So the generator will get better and better, and the job for discriminator will be harder and harder. And that's why if it's looking to find a boundary around your real data, the boundary will get closer and closer to the actual training data. So then we can say you will have an even better version of the thing that you have seen in the previous workshop, just by having that adversarial process. The other thing that I want to talk about is what is then conditional GANs. Because as you saw here, as you saw in the GANs, the base of generating sample was based on a prior, which can be just a noise. But for us, we want to be able to generate a good sample, something meaningful. We want to be able to cover all the data, all the training data, all the distribution of it. So instead of just passing random noise, you can have some more information for generator to help it or guide it to make a sample which is similar to the thing that you're looking for. So here, let's say for MNIST, the generator should just be able to produce an image. It can be 1, can be 2, it can be 3, but it can be anything basically based on the noise that you're passing, right? But here you can pass the label as well, the class as well. So it will be conditioned based on some extra information that you're passing to the generator, and then the generator should be able to make a sample given that extra information. And even we'll give that information to the discriminator as well. But even the discriminator, given that class and that label and the generated image, should be able to tell the difference, to say that okay, if it's actually working or not. So we are kind of making the job for generator harder and for discriminator easier a bit, because here, even if a generator was able to generate a good number 5, but the actual label was 2, the discriminator should be able to tell the difference easily, because the 2 won't match that image, but for the real data it will always match. So then the generator should actually generate a sample using that condition that you're passing in a way that you'll be able to fool the discriminator. So I talk about that because that will be the building block of most of the model that has been generated for anomaly detection. So something like that, which is one of the model that has been used for finding anomaly in your image. So the thing that is doing like that is kind of like a conditional GAN, which basically you're passing an image, and the whole image is the actual condition, because we don't have any label here. So we are using the whole input as a condition, and then you're passing it through an encoder. It can be a regular autoencoder, or it can be a more complicated version of it, which was variational autoencoder. So it doesn't matter, it can be anything. So as far as you have a model, given the image, we'll maybe compress it, and then we'll decompress it. And then, so the first part is exactly like autoencoder or variational autoencoder. But in autoencoder, we were the one who were telling the difference by some measurement. It can be the distance between them. It can be just MSE. It can be just by saying that, okay, that's my number, that's a new number, what's the difference between them? That's a residual error. But here, we're saying that instead of me defining a metric, I can have a discriminator, and the only job that the discriminator has is to be able to tell the difference between the input and the reconstructed one. So if it can, so it means then the decoder, the autoencoder should get better and better as at making a new sample, which is a reconstructed one, super similar to the input one, so it can fool the discriminator. And the discriminator, and discriminator will get better and better every single time, because it wants to be able to tell the difference as well. So it's like a game theory thing. So because of that adversarial process, then the autoencoder will get better and better, the discriminator will get better and better, and then once we have a new image, a new sample, you can pass it, and then the discriminator should be able to say that, okay, was it real or was not? And then you can just use that score as a metric of what is anomaly or not. So if you have a new sample which is not from your distribution, then that generator part, which is autoencoder, won't be able to generate a sample which is similar to the input or to the training data, and then the discriminator should be able to tell the difference. And again, I just want to talk about the previous session as well. In previous session, I shuffle it. Here, I'm using the reconstructed one, and then I'm passing to discriminator, and the discriminator should be able to tell the difference. So see, I'm still, if you ignore the generative part, what I'm talking about is mainly about the discriminator, which is a binary classification, and instead of me doing the shuffling, I'm using the reconstructed from the autoencoder, which the autoencoder will get better and better. And because the generator part can be any autoencoder model, it can be just autoencoder, it can be variational autoencoder, even it can be adversarial autoencoder as well. So it's kind of like a mixture of these two. And if you want to even make it a bit more complex, there are other techniques as well. They're saying that why should we have the autoencoder just as a generator when we can have it as a discriminator as well? So this basically is like they're even making the job harder for the model to be able to easily reproduce the input. And that's why they're saying that, okay, try to generate a new data. And then for the discriminator, they were saying that, okay, that's a generated one, and that's the actual data. No, reproduce it again. And then they're comparing the distance between the generated one. Maybe we can say the double generated one for the double for the maybe noisy one, and then to be able to tell the difference. So they're kind of adding another layer of complexity for the model. The reason for that is we want to make sure that the sample or the thing that we are calling outlier is actually outlier. So in autoencoder, the whole idea is if my autoencoder can't reproduce it, or if the loss or the construction loss is a bit high, it outlier. But the thing is, you might say, okay, it's not always working. That's why we said, okay, we're adding restriction to the autoencoder and to enforce it to map it to some prior. And then you can use both of these score. Or here, you can just say, see, I want to make sure that if you pass it to two, they call it like a dual autoencoder, the end image will be still similar to the input one. If I manage to learn the distribution of a data to be able to generate and to be able to tell the difference using two autoencoders. And there was another paper which even go a bit further and says, look, see, I want to use all the metrics that I can. They call it GANomaly. It's basically a combination of GAN and anomaly detection. It's basically saying that, okay, for generator part, I want to have autoencoder, which basically, as I said, is a conditional GAN. You're reproducing an image as a generated one. And then the bottom one is the discriminator, which the only thing that it's trying to do is to tell the difference between the input and the generated one. So that's why the first loss would be the loss of adversarial, the D, the distance between the two f of x. But the thing is, then you're saying that, okay, I have an autoencoder and I can actually use the distance between them as well. So that's the first, the loss of encoder. And you can say that because I have an embedding space in between, I can use that one as well, right? Because for variational autoencoder, we said that you can use it. So here, it makes another encoder on top of the output image to come up with a new embedding which calls Z. And then it comparing that one as well. So it means then it has 3 score, checking all of them to say that if that new sample is different in any way, if it's different when I'm encoding it to the Z, or when I'm reconstructing it, or when the discriminator counts the difference. So you're checking all the things that you can check to make sure that your input data is as real as it could be. So that's what I'm saying. So it is like adding more layer of complexity to the model, which when you have super complex anomaly or layer, sometimes you have to do that. Let's say when you're talking about a device that is generating some number and sometimes it will be faulty, maybe you don't need that. But let's say whenever we are talking about insurance company and we are talking about human will do its best to be able to fake a claim which is super close to a real one. It will be super hard to be able to tell the difference between a fake one, fraud one, and the actual real one, because a human, intelligent person was behind it, was working on it to make sure that it's super close to the real one. And even in GAN, we're enforcing the kind of generator part to be able to make as real, as similar to the real data as is possible, and still we should be able to tell the difference using different technique and number. So the more complex the more complex is your data, or the more complex is your layer, if it's human generated or if it's just like a from device, then you can decide which model you should use. And if it's super complex and it's super complex to catch, maybe all these models will help you. But again, I'm going to say that not all the time and not always. So as I said, so there's a catch here because it's a super complex model. Training this model is super hard, and even to be able to say what is the best, I don't know, prior for either the autoencoder or here to be able to train everything would be super complex. So you should be able to actually worth it to be able to use it. So there are lots of other techniques based on GAN as well, and every single time I guess they're trying to make it to be more fancy and more complex. But all the thing that they're trying to do is they're trying to make sure that whatever they're generating can learn the distribution of the data good enough that if you are different from the training data, they should be able to catch it. The other thing that I want to talk about is actually hybrid models. So the deep hybrid models for anomaly detection use like a deep neural network, mainly we can say autoencoder, or it can be CNN or LSTM based on the type of the data that you have as a feature extractor. And then the feature learn within the hidden representation of your autoencoder or whatever model you're using will be as an input to some traditional anomaly detection algorithm, like 1SVM. See, it means instead of just using autoencoder or rational autoencoder as is to be able to find anomaly, you can just use the embedding layer of it. Because as I said, that embedding, you're saying that you can compress everything to that, and that would be like the most essential feature that you can get from your data, and then you can pass it to one of those classical models that we talk about, like 1SVM, isolation forest, clustering, because then you can just use it as a dimension reduction, and then you can just use it for any of those techniques. So even if you have sequential data, you can use LSTM, map it to a fixed length input, and then just use 1SVM or isolation forest for it. That's what they call like a hybrid. And the other one that I want to talk about, which is similar to the other one, the hybrid one, is the transfer learning based anomaly detection, which is kind of basically the same thing as a hybrid one. So because you can say the following the success of all those transfer learning, which they were trying to get a representation from some model, from some pre-trained model, Even here, they try to employ this pre-trained transfer learning as a feature extractor to be able to get a good number for anomaly detection. It means, let's say, even if you, here I would just start trying to say that, let's say, even if you don't have enough sample, you can train a model on maybe let's say ImageNet if you're dealing with the image, or a huge text from, I don't know, all the Wikipedia. Train a model and then use it for your own sample data to be able to fine tune it to come up with a better representation of it, and then use that representation, a super low dimensional representation of the input, and then use any method like KNN or OneSVM or anything. So it means a hybrid one, which you are using the deep learning part, which you're using maybe, let's say, a huge amount of data that is out there to kind of pre-train the model and then retrain it for your own data to come up with that embedding space, and then use it with any other technique that you know, like KNN, OneSVM, oscillation first. So basically, all the things that I talked here was different way that you can find any kind of outlier in your data. There are tons of other methods like that, which basically the base idea of all of them are similar to all the things that you have discussed, is how can you learn your data in different way. We talk about the statistical models at the very beginning, and then we said how can you learn the boundary like OneSVM, and then even if you can do clustering, KNN, and then GM or even GMM, fitting a GMM model. And then today we said that even you can just compress it, decompress it, the construction loss, or you can just use a part of it as a self-supervised one. You can predict the future, autoregressive one, or if even the more complex version of it will be GAN, that you want to reproduce, you want to be able to tell the differences in the discriminator, and you want to try to have a good generator so you can make a good fake or anomaly or any something similar to your trained data, but not your trained data, and still be able to tell the difference. So all these techniques can be used for finding outlier in your data. And I just want to stop here and say that that's the kind of wrap up for this session. For the hands-on experience, we will try to implement some of these models with a more complex data set and see how they're working and how can we actually use them in different places.